speaker okay, is Pablo Raúl Stinga from Iowa State University, who will talk about Harnack inequality for fractional nondivergence form elliptic equations. Thank you.
Thank you very much, Stefania, for the invitation. Thank you also the organizers for this opportunity to present here in this very nice seminar series that I follow very closely. So yes, I'll talk about some work I did with Mary Vaughan, who was my PhD student, and she's now a postdoc at UT Austin, working with Stefania and Luis Caparelli. So let me just begin with a basic non-local equation or integral differential equation. So you have u of x minus u of z, there is a kernel, and the right-hand side f, and you integrate in omega. So two features of the non-local models. One is that what happens far away affects the local behavior instantaneously, right? So at the point x, everything that happens in omega affects the point x through the interaction kernel. And the other feature is that there are no derivatives of u involved. So both these aspects make these models quite useful, and we know nowadays we have a lot of applications. So in peridynamics, for example, they try to model fracture in elastic materials. So they say, well, instead of using the usual elastic equations, right, which are essentially the wave equation, they use a non-local model, right, an integral model where there is a kernel K that says how the atoms interact with each other. And then since the kernel that they choose is integrable, then it accepts, the solution accepts discontinuities. So then you can, try and model discontinuous functions, right? Fractures in the material. And the other application will be for image processing, right? Again, an image is a bunch of characteristic functions. So there are some works also where they're trying to do image processing with non-local equations. And the fact that it's not local also, the pandemic, we can talk about the pandemic, right? What happens far away affects the present position. The spread of information, for example, in discrete settings, you have a lattice, right? And what happens far away in social media, right? Somebody at the other end of the world says something that affects my behavior, finance, and of course, there is a theory of fractional derivatives that are non-local. Okay, this is just like a basic introduction. So what is the basic non-local operator? Is the fractional Laplacian, right? So the fractional Laplacian is to this integral differential equations what the Laplacian is to second order PDEs. So the fractional Laplacian, right, is defined for S between 0 and 1. Using the Fourier transform, you take the Fourier transform of u, multiply by the Fourier multiplier of the Laplacian, which is psi squared raised to the power s, and then you invert back, right? And then we know that is given also by this integral differential formula, right? This is the kernel, and there is principal value because this kernel is not integrable. So there is some cancellation here that has to happen, right? U has to have some regularity for this integral to converge. And we see that the fractional Laplacian is a non-local operator and is of order fractional differential order 2s. And then there is this intermediate formula here, right, that involves the heat semigroup generated by the Laplacian acting on U. So you look at V of xt, which is this semigroup acting on U. This just represents the solution to the heat equation, right, with initial temperature U. We know, right, that that's just convolution with the Gauss-Weierstrass kernel. GT, right, the Gauss-Weierstrass kernel. So, in fact, using this Gauss-Weierstrass kernel here, right, and applying the Fubini theorem, you can pass from the semigroup formulation to the points-wide formulation without any problems with this constant explicit. You can compute it explicitly. And to pass from this formulation to this one, it's just a numerical formula I'll show later in the slides. So there are all these descriptions, Fourier transform, semigroup, and pointwise formula. Okay, so what about random processes, right? The Laplacian, we know is infinitesimal generator of Brownian motion. So here I'm thinking that you have a particle that moves in one dimension, and the probability to go to the right is 1/2. The probability to move to the left is 1/2. So the probability to be at the point X by the law of total probability is the probability of being on the left and the probability of being on the right, right? So you have 1/2 U of X plus H plus 1/2 U of X minus H. And this is just, the mean value property. U is the average at X plus H and X minus H. So when properly rescaled, when H goes to 0, you recover a harmonic function, right? Now, what happens if you do random processes in heterogeneous media, right? At each point, the probability to move, right, left or right or whatever, changes from point to point. There's no 1/2 and 1/2 anymore. So, so in 2 dimensions, for example, you move up and down, right or left, with different probabilities, and at each point, the probability changes. So there you end up with an infinitesimal generator, right? Will be a non-divergent form elliptic operator, right, of second order with coefficients Aij. Now the fractional Laplacian is the infinitesimal generator of a random jump process. So in this case, now say the particle, the one-dimensional particle U is allowed to jump everywhere, right? In the real line. Say we have a mesh here of size H, right? So I'm allowed to jump anywhere, right? And the probability of being at the point X by the law of total probability is, right, the sum of the probabilities of being at any other point. And this is the probability of jumping from X to the point HK, right? And this is a kernel that sums to 1, right? So if you choose the appropriate kernel here, probability kernel, and then you take H points to 0, you can recover the fractional Laplacian. So now what happens if you do random jump processes in heterogeneous media, right? Instead of being homogeneous like here, right? At each point, this only depends on the distance between X and HK. You have a kernel that is changing from point to point, right? And on the next point, I have a different density here, K. Then you can recover the infinitesimal generator will be a fractional power of a non-divergence form elliptic operator. Okay. So these are the objects we're going to look at. So again, as I said, this is joint work with Mary Vaughan, my former PhD student, and they appeared in this journal last year. So what is the main result? So here is the setting. So we look at a uniform elliptic non-divergence form operator. Here Aij are the coefficients, right? The Ij's in trace form in some bounded domain omega, subject to 0 boundary condition on the boundary, and the coefficients held there and bounded and symmetric. So the theorem says that we take S between 0 and 1, a non-negative solution to this fractional problem in a ball, right? Then in a ball of radius r, then we have Harnack inequality, right? The supremum in a smaller ball, kappa r, is controlled by the infimum, plus the right-hand side properly rescaled r to the 2s, right? So kappa here is less than 1, depends on n, the dimension, s the fraction, and the ellipticity of the matrix Aij, all right? And then one can also prove that solutions to the fractional problem in omega are locally Helder continuous. Okay, so this is the result I wanna talk about. So there are several things here. First of all, how you really define this fractional power, right? That's one thing. The other thing is how to prove the Harnack inequality. No, so let's. But before we go to that, let's look at other applications. I already mentioned the random jump processes, but one application that I'm very interested in is the fractional Monge-Ampère equation. So we start with the Monge-Ampère equation. So if U is convex and C2, then one can write the determinant as an infimum, right? So the determinant of the Hessian as an infimum. So you raise to the 1 over n and multiply by n, and that can be written as the infimum of the Laplacian of these linear transformations of U acting on a inverse of X. What are these A's? are just symmetric matrices, positive definite, that have determinant 1. Okay, so if you pass the Laplacian through, you get the trace of a squared, d squared, u. All right, so the determinant of the Hessian to the 1 over n is a concave operator, right? It's the infimum of linear operators, where you take the matrix is symmetric, positive, and with determinant 1. And this is easy to see. I mean, on the left, from the left is always less than or equal than the right, because here you have the product of the eigenvalues, and here you have a linear combination of the eigenvalues. So that's the arithmetic mean, geometric mean inequality. And it's easy to see that for a squared equals something like the inverse of the matrix of cofactors of V2U, you attain infimum. It's very easy to do. So now, Caffarelli and Charro replace this Laplacian by a fractional Laplacian, right? And take the infimum again, okay, in the same class, and they denote this operator ds, and they call it the fractional Monge-Ampère operator. Okay. So if you write down the integral formula for the fractional Laplacian here, this is what you get. So you get the kernel of the fractional Laplacian is being deformed according to this matrix is A, right? And you take the infimum among the class of matrices A. And they prove that, you know, when S goes to 1, you recover the determinant to the 1 over n. Okay. So they take this operator, they study some properties, the Dirichlet problem, the Poisson problem, and so on. So one aspect of this is that doesn't fall in the classical, by now classical theory of Caffarelli-Silvestre, because the operator is the general elliptic, right? The matrix is here, A, can degenerate in dimension 1. Dimension 2, you have epsilon, 1 over epsilon, as determinant 1, positive definite, but the minimum eigenvalue goes to 0 and the maximum eigenvalue goes to infinity. So in principle, this is very degenerate. Well, exactly as Monge-Ampère. Right? But they prove that if you use Lipschitz semi-concave, the fractional Monge-Ampère operator is bounded below, away from 0, say locally in a ball B, then the equation becomes uniformly elliptic. So you don't need to take the infimum among all positive definite matrices of determinant 1, but only those that have minimum eigenvalue bounded below by little lambda. So there is a little lambda here, depending on the ball, on eta naught, the semi-concavity constant of U, the Lipschitz constant of U, such that in that ball, the operator can be computed with these uniform elliptic matrices. Okay. So after you have these, right, it's like in Monge-Ampère, right? After you have these, now the Caffarelli-Silvestre theory kicks in to obtain regularity. Okay, so this is exactly the thing you need to prove to apply that regularity theory. But how is it that we have this non-divergence form operator to the power S appearing? So the computation we do in this case, in the uniform elliptic case, we write down this, right? This is a linear transformation of the fractional Laplacian. So you can write it as this is a linear transformation, right, of the Laplacian to the power S. No problem there. Now, the infimum at each x, since this is an elliptic class of matrices, is attained. So at each x, there is a matrix A squared that attains the infimum. All right. So this is just the linearization, right? This is a linear operator, right, acting on U. So the fractional power of an operator in trace form that has some coefficients changing from point to point. Okay. So it's how you end up with these fractional powers in this setting. All right, more applications. Well, if you do the Signorini problem or the problem of semi-permeable membranes, and you have a heterogeneous diffusion instead of just a heat equation, then on the membrane, you can obtain a fractional equation of this form also. Or even if you do like a transmission problem for fiber materials, so say you are in a flat interface and your material is made of fibers, vertical fibers, right, changing from point to point. Then when you look at what is the equation on the interface between these two materials, it's a combination of fractional equations of this form. Question, is V Helder continuous? not here, right? Here is just bounded measurable. We don't have control in principle. So yeah. And then the other application back again to the processes, to the diffusion processes. If you have a diffusion process xt kill on the boundary that has this infinitesimal generator, if you do the subordination of this process by an S-stable subordinator, T sub t, then the subordinated process has infinitesimal generator, the fractional power. Okay, so and then they use this in finance, theory of diffusion processes. Okay, so these are the applications. Now let's go to the definition of the fractional power. Right, we cannot use the Fourier transform. Obviously, there is no spectral decomposition. Right, in principle, the spectrum is complex value. So how do you define this operator is not symmetric? Right, there is no natural Hilbert space to work with. So what do? We use this method of semigroups. So what is the setting? We take a bounded domain, which is a Lipschitz uniform exterior cone condition. It's enough. The coefficients, let's assume for now that they are continuous and bounded, symmetric, and of course uniformly elliptic. Well, we're looking at functions that are zero at the boundary. So let's look at this Banach space C0 of omega, continuous up to the boundary, that are zero on the boundary. Then the non-divergent form operator in this domain, so domain is continuous functions that are zero on the boundary, and W2n, such that, you know, when you apply the operator, you go back to continuous and zero on the boundary. This operator L in this domain generates a C0 semigroup denoted by e to the minus TL on this Banach space C0 of omega that has exponential decay. The exponential decay is because of the zero boundary condition. So it's a result of Arend and Schatzle. So what is this semigroup again? What does it mean that it generates a zero semigroup? It means that if you take any U in the domain of L, right, in this space, then this operator, right, this family of operators acting on U depends on T, this is a function now, is the unique strong solution to the heat equation, right, for the Aij operator, right? So we have heat equation, zero boundary condition, right, on the boundary of the cylinder, and the initial condition is this U, right? And the exponential decay means that for any U in the Banach space, the semigroup acting on U in L infinity decays like e to the minus epsilon t. All right, the L infinity normal of some n. That's the exponential decay. All right, so why do I need this semigroup to define the fractional operator, right? So now, for U in the domain of L and X in omega, we can define the fractional power using the semigroup formulation, right? So you have the semigroup acting on U minus U and so on, right? So this is like in the book of Yoshida, right? Functional analysis. This is called the Balakrishnan formula. Okay. So so where does this formula come from? You know, if you take a positive lambda and you want to write lambda to the power s for s between 0 and 1, you can write it in this way using the gamma function. Okay, so this is very simple to check. You just do a change of variables here. The lambda replaced by r, whatever, and then you see that the lambda to the s pops out. And when lambda is 1, this is exactly the formula for the gamma function evaluated at minus s. Okay? So this is just replacing lambda by the operator f formally, right? Just replace lambda by the operator f. And as I showed before, this is exactly what happens also for the fractional Laplacian. Here we have the semigroup generated by the fractional Laplacian, the solution to the heat equation. All right. So for the fractional Laplacian, if you put here psi squared, right, the Fourier multiplier of the Laplacian, then you will have here e to the minus t psi squared, which is the Fourier multiplier for the solution to the heat equation. Okay. So for the fractional Laplacian, the semigroup formulation is easy to check using the Fourier transform. But here we don't have Fourier transform, so we just take the semigroup and plug it in here. Okay, so this as a function analysis definition is fine. What is the advantage of the semigroup is that when you have a heat kernel, you can say more, right? So for example, if the coefficients are held continuous, then you have a heat kernel. So this solution to the heat equation can be written as the integral of little u against the kernel. And then you just plug in here and apply the Fubini theorem, and you get this formulation, the point-wise formulation for the fractional operator, right? So this is a non-local operator living in omega. Here we have the interaction kernel, and the kernel can be bounded by the kernel of the fractional Laplacian. This is because of the estimates for the heat kernel of the operator L. And there is this extra function here, B, that is bound. And this function appears because you have 0 Dirichlet boundary condition. If you had Neumann boundary condition, this couldn't be here. Okay. All right. So there's the expression of the operator. And now, well, we want to prove Harnack inequality. So for that, we're going to do the extension problem. So let's just recall the Caffarelli-Silvestre extension for the fractional Laplacian. Okay, so if you have a function u of x in Rn, and then you do the extension, solving this general elliptic PDE. So u at the trace is little u, and then you extend capital U, solves this elliptic equation. So the Laplacian here in X. And I wrote the extension equations in non-divergence form, okay? Because my operator L is in non-divergence form. There is another version in divergence form, right? Perhaps people are more familiar with that, but with a change of variables, you can eliminate the term, the dy term that usually appears, and you have this non-divergence form equation for the extension. So you have this z to the 2 minus 1 over s appearing here, this is z of u. And then you take the normal derivative, right? Again, when you write this in non-divergence form, the conormal derivative condition in the divergence form changes into just the normal derivative, okay? At z equals 0, you recover the fractional Laplacian. All right, so that's Caffarelli-Silvestre. They prove this, you know, with the Fourier transform. But then later on, with Torrea, and then with Galea-Miana, first with Torrea for Hilbert spaces and Galea-Miana for Banach spaces, we prove that this extension is a very general thing. So say we take a Banach space X, and you take a function in X, right? And then let's suppose that L generates a C0 semigroup on X, right? So you have this semigroup, so essentially you can solve the heat equation for L. And so then you have the semigroup. With the semigroup, you can define the fractional power, as I showed before, right? Up here, you can define the fractional power with the semigroup in general, right? And then if you solve the extension problem, when instead of here Laplacian, you have your operator L, right, with initial condition u, then the normal derivative coincides with the fractional power of u. Okay. Of course, here u in X should be in the domain of the fractional power, okay, for this to be true. Yeah, so as I said, if you want to work with Hilbert space, that's the theory with Torrea, and then with Galea-Miana, we did it for general Banach space, even like more general than C0 semigroups. There is this class of semigroups called integrated semigroups. So you can also do it for generators of integrated semigroups. So this is extremely general, right? And the idea, of course, you cannot use the Fourier transform anymore. So what we look at is that this problem as a vector valued Bessel equation, right? Because, and then, you know, that's the point of view we use for this, right? To solve this thing. And yeah, anyway. So as I said, this is very general, so applies to many things. So for numerics, right? If you look at the Dirichlet Laplacian or the Neumann Laplacian about the domain here, you can do the extension and do the numerical, right, simulation. Manifolds, again, if L is the Laplacian on a manifold, you know, the Heisenberg group, a Carnot group, or a Riemannian manifold, or the sphere, or whatever you want, then you still have the same characterization. space-time. So L here doesn't need to be just an elliptic operator, could be like a parabolic operator, like the heat operator or a general parabolic operator. And then you can also like do discrete settings. So L says the Laplacian, the discrete Laplacian on a graph. Then you can study its fractional power and so on. So it's very applicable to many scenarios. So we're going to apply it to our case. So what will be the extension product in our case? As I said, we put the L and then the Z part equals to 0. Right? This is our L, the non-divergence form operator, with initial trace or initial value little u, and of course 0 on the boundary, because that's where the domain of this lies, right? So if you solve this problem, then the normal derivative will be the fractional power of this operator. Okay, the fractional power of this operator. Okay, and say now acting on U. So if you have a right-hand side F, essentially what you need to study is this equation with this boundary condition, 0 on the boundary, and with normal derivative prescribe F, right? And then you need to study what happens on the trace, because the trace will be the solution. So with this, we can prove Harnack, and the idea for Harnack is to prove Harnack for capital U up to Z equals to 0, okay? So say you look at the supremum of little u in B kappa R, in ball, and then, well, the capital U coincides with little u. So this is what we have. And now U lives, in the upper part of the cylinder. So I can, if I extend U above, I look at U above, I have the supremum increases. If I have Harnack inequality for U up to the boundary, I can apply Harnack inequality for capital U, right? And then the infimum, if I restrict back to little u, the infimum increases, right? But then on the trace, the capital U is a little, all right? So that's the strategy. So what do we need to prove? In fact, we need to prove Harnack inequality for capital U, solutions to the extension equation with this Neumann boundary condition. So that's what we need to do. Okay, so let's look at that equation. So the U was living in the upper part, in the upper cylinder, right? Z positive. If I do an even reflection, the even reflection will solve this problem with modulus of Z here, right? Absolute value of Z. And then the normal derivative still will be F, right? So this is the question I need to look at. I need to prove Harnack for this, up to Z equals to C for the trace. So what happens if S is 1/2, for example, right? This is not here. Then as a single equation, even if Aij is the Laplacian, right? Identity matrix. For a single equation, this is what you have. You have an elliptic equation with a singular right-hand side, okay? If S is 1/2. Now, if S is not 1/2, it's even worse, right? You have this degeneracy or singularity, okay? So how are we going to attack this? I mean, it doesn't fall right into the general theory that we know. Well, the idea is that this equation, the extension equation, will be comparable to a linearized Monge-Ampère equation. So let's look at this convex function phi of x and z, strictly convex. So x squared, and then you have this z to the 1 over s, right? So if you linearize Monge-Ampère on this phi, this is what you get, right? The linearized Monge-Ampère is a trace of the inverse Hessian of phi acting on a u, right? D to u is this operator, right? Is the extension operator where you have here the Laplacian. This comes from this x squared, right? The Laplacian, and then the z part is 2 minus 1 over s comes from this other piece, right? When you compute this inverse. Okay, so for this phi, the linearized Monge-Ampère equation is the extension equation, right, of Caffarelli-Silvestri. So our equation is not exactly that because we have the coefficients, right? So, okay, our equation is comparable to linearized Monge-Ampère equation. And you say, okay, now I have a linearized Monge-Ampère equation. Perhaps I can apply the whole theory, right? Because there is a theory of Caffarelli-Gutierrez from '97 that they study linearized Monge-Ampère, right? So if phi is convex and smooth, you have a 0 right-hand side, then they prove Harnack inequality, right? The problem here is that phi is not smooth. You have the singularity at z equals 0. On the right-hand side, if you want to look at it as a single equation, it's also singular. Right? It's a singular measure concentrated at z equals 0. So, okay, as a single equation is this problem, and then otherwise you have to look at it as a Neumann problem, right? So we're gonna go back to Caffarelli Gutierrez and just use their theory. Okay, so well, you know, if you have linearized Monge-Ampère equation, there is a geometry that you need to follow, right? That is you know, made evident in the paper by Caffarelli and Gutierrez. So what is that Monge-Ampère geometry? Right now, this phi, right? You have x squared plus z to the 1 over s. Instead of looking at the Euclidean balls or cubes, you got to look at the Monge-Ampère sections, right? So what is a section centered at a point or radius r? So if you look at this, phi of x0 is 0 minus gradient times this part. This is the tangent plane of phi at x0 is 0, right? So what you do, you look at a point, and you look at the tangent plane of phi, and you raise that tangent plane by r, right? The sublevel set of that is a section, right? So if phi is x squared, these are Euclidean balls, right? With radius, I think, r to the 1/2. Yeah. Okay, so you have to replace the Euclidean balls by the sections of this convex function that's driving here the coefficient, right? And then there is a quasi-distance, right? So it's just the first order expansion of phi minus its Taylor polynomial, first order Taylor polynomial. That's the distance between 2 points, right? So this is a quasi-distance. It's not really a distance. And then there is a measure, right? Which is the Monge-Ampère measure of a set E, right? It's just the measure of the subdifferential of phi at E, and this we can compute this, and it's just the determinant of the Hessian of phi. Okay, integrated over E. Okay, so this is the space of homogeneous type where we had to work with, right? It's a quasi-metric space with this Monge-Ampère measure, and the balls are the Monge-Ampère sections. Okay, so this is where we look at the extension equation. So here is the theorem. It says this is Harnack for capital E, right? That's the thing that I wanted. So if you have a coefficients and the U is non-negative, right? A classical solution to the extension problem now in a Monge-Ampère section instead of a ball section. Then the supremum in a smaller section is controlled by the infimum plus r to the s, the scaling, the L infinity norm of the Neumann condition at z equals 0. All right. So if the section is far away, right, doesn't cross 0, this term is not there. Okay. So this is the Harnack inequality we want. Right now we can prove the Harnack inequality for little u, the solution to the fractional problem. Okay. So what is the technique to prove this this theorem in this general Monge-Ampère geometry where the phi is not smooth and you have this singular right-hand side? So the ideas are based on the method of sliding paraboloids that Ovidio Sabin did for the uniform elliptic case in 2007. Okay, so well, what are these paraboloids? So okay, so for Sabin, paraboloids are just quadratic polynomials, because the equation is elliptic. But for us, we introduce this new class of paraboloids that follow the Monge-Ampère geometry, right? So what is a paraboloid? A concave paraboloid of opening A and vertex, say, XV, ZV, right? Is just minus A times the Monge-Ampère distance between the vertex and any point, right? So if delta is x squared, right? The Euclidean distance squared is just quadratic polynomials, right? So this is a paraboloid now for us, the Monge-Ampère paraboloid. Okay, so there are three main steps for the proof of Harnack inequality. So here is the sliding paraboloids as in Sabin, right? So we take these paraboloids, P, Monge-Ampère paraboloids, we slide them from below until they touch the graph of U, okay? And then at the contact points, that's where we use the equation to control the measure of the contact points by the measure of the set of vertices. Okay, so you have a set of vertices, you take those vertices, take those paraboloids with those vertices, and then slide them up, right, until they touch. And then you see the measure, you control the measure of the contact points by the measure of the set of vertices. This is the replacement, let's say, of the AVP estimate, okay? Okay, then what you do, okay, then you increase the opening of the paraboloid. So you make the paraboloids narrow, narrower, and narrower, right? And then, well, if you make the paraboloids narrower, you will be able to touch the function at more points, right? The paraboloids like that, maybe you touch less points, but if you narrow that, you're touching more points, right? So by doing that, you will see that the set of contact points almost cover the domain in measure, right? So if U is like U at a point at the center of the section, then, I'm sorry, if you normalize, if you look at U at a point, then at nearby points, U will be like U at the center, right? And see, you have this control of the contact points, then you see that except for a set of very small measure, U is almost like U at the origin, right? Because you have the control. And for this, you have to do barriers that take into account the Neumann condition, and you do a covering lemma for Monge-Ampère sections, which is just a covering lemma for the kind of Vesikovich type or Vitali type. Okay, so you know that essentially in all the domain, except for a set of very small measure, U is comparable to U at the center of the section. And now you say, well, if U is very large, at some point, with respect to the center of the section, then using the same methods, if U is very large, then U will be also very large in a set of positive measures. You use the same method, the same ideas, and that will contradict the idea, the fact that in most of the set, U was comparable to U at the center of the section. Okay, so these are the steps for the Harnack inequality. So let me talk about the first point, which is the control of the measure of the contact points by the measure of the set of vertices. So here is the main lemma. So say you have a super solution to the extension problem in a section. We don't have Neumann, so f equals to 0, say, for simplicity. And then we take vertices in a closed set. Again, we slide those paraboloids of opening A with those vertices from below until they touch the graph of U for the first time. Now suppose the contact points are all contained in section S, then the Monge-Ampère measure of the set of contact points is controlled by below by the measure, Monge-Ampère measure of the set of vertices, okay? By this universal constant that depends only on dimensionalities. So of course, if f is non-zero here, you will have to control what happens when you touch at z equals 0, okay? That's what I'm saying here. Because when z is 0, right, there is no equation, right? The equation is just for z different from 0. So that's something that needs to be taken care of. And the other thing here is for Sabin, of course, he's doing the uniformity case. He has the Lebesgue measure, right? But for us, our measure is not comparable to Lebesgue measure. So the estimates are done in Monge-Ampère measure. So we're following all the geometry, right? And as I said, you use these to control the growth of U to show that, you know, if you normalize U at the center of the section is 1, then, you know, for most of the domain, U will be less than a constant, a universal constant. And then you continue with the next steps in the proof of Harnack. So this is the main lemma. So let me show you like a little bit the idea of the computation for this lemma. Say the vertices is a set B, XVZV, the vertices, and the contact points are X0, Z0, and you slide these paraboloids and say you'd always touch on the side where you have equation. So if P touches from below at the point, then you can, of course, compute the polynomial explicitly. So here's the distance between the vertex and xz, and then the distance between the vertex at the touching point plus u at the touching point. Okay, it touches from below. All right, since it touches from below, then the gradient of u minus p at this point is 0. So you have this inequality here, and you compute the gradient of p. It's just minus a here, right? This difference at x0 is 0. The gradient of phi. Phi is our convex function leaving the Monge-Ampère, linearized Monge-Ampère. Okay, so now with this, we create this Lipschitz map T that is a contact point to vertex point. So you take a contact point, right? X0 is 0. And you look at, so you pass this to the other side, right? Divide by A and pass this gradient phi to the other side. That's what I have here, right? That is exactly the gradient of phi at the vertex, right? So given the contact point, right? You get the vertex, all right? So this thing here, this map T takes contact points into vertices, all right? Well, you get the gradient of phi, but you get the vertex. Okay, and since you're touching u from below, the Hessian of u is controlled from below by the Hessian of phi, right? Minus a Hessian of phi. And then you can use the equation to prove that the Hessian of u is controlled from above by the Hessian of phi times a. All right. This is using the equation, this part here. And of course, this parabola is phi, this polynomial is p and this phi behaves well with the equation, right? Our equation is not translation invariant, right? These polynomials are not translation invariant. So this p and this phi, they behave very well with the equation, okay? So they go with the equation. So if you try to do this with the usual parabola, it doesn't work. Okay, so the idea now is just to use the formula for Lipschitz maps, the area formula for Lipschitz maps. So the measure of B, right? Also remember here, B is the vertices, right? Is the gradient of phi at B, right? But the gradient of phi at B at the vertices is this map, right? T of A. And A is a set of contact points, okay? So this is the connection, right? To pass from vertices to contact points is exactly this formula. All right, so T of A, you integrate T of the vertices, and now you use the area formula. So you integrate over A the determinant of the gradient of T. Now T was phi plus 1 over A U, so the determinant of the Hessian of that. And now we saw using the equation that this is comparable to the D2U over A is comparable to D2 phi. D2U divided by A is comparable to D2 phi using the equation. Okay, so we replace that by phi with a constant, and that's it. This is the Monge-Ampère measure of the set A times A. Okay, so that's the computation. As I said, then you have to be careful if you touch from below at the z equals 0 point. Right? But I just want to show that how the computation works in this case. All right, so that's it. Thank you very much for your attention.
Thank you very much, Pablo, for the beautiful talk. Thank you. Are there questions?
Yeah, I've got a question. So Pablo, in the classical case, for non-divergence form equations, there's a C1 alpha regularity in 2 variables. I was wondering if in the non-local case, maybe for S sufficiently close to 1, depending on ellipticity, one can get beyond the Harnack in 2D, get C1 alpha.
Yeah. Yes, I mean, yes, one probably can, but yeah. I mean, I haven't thought about that, but yes, you see, you know, we use linearized Monge-Ampère equation heavily, so it looks like whatever for local equations degenerate or can be transferred to non-local. So You mean so 2D for the fractional, so the extension will be 3D, right? So
right.
yeah,
so that's why it's
yeah. I don't know. That's a good question. Yeah.
Okay.
Yeah. With Mary now we're like doing the Schauder theory. And when the coefficients are held there, then you want to get the sharp Schauder theory, and still is a lot of technicalities there because of the Monge-Ampère, structure. And even for viscous solutions, it's not even clear how to define them properly. Again, because of the Monge-Ampère. When you realize Monge-Ampère is usually W2N solutions.
Right.
So there's not much viscosity around. So yeah, there are many things here that need to be seen.
Okay.
Yeah, good question. Yeah.
Thanks.
Other questions? Well, if no more questions, thank you very much, Pablo, again for the beautiful talk. Thank you.
Thank you, Stefania. Yeah, thank you, everyone.
Thank you.